The goal is really to have to engage with everybody in the room and to exchange ideas and see if there is a consensus or not a consensus, but at least we can define where the consensus is coming from. And I think now we're going to start with pluripotency. And so the first question is, should pluripotent state be defined molecularly or functionally?
I mean, personally, my view is it fundamentally has to be a functional assay. I mean, what we mean by pluripotent cell, obviously precise meaning varies between different people, but it is that it can do various things. The markers are all surrogates. It's very good that they tend to correlate, but we don't know them necessarily well. And just as one example crosses my mind, SSEA4 is widely used as a stem cell marker. It's a blood group antigen belonging to P blood group system, and for stuff we did years ago, about 1% of the population should be SSEA4 negative. So there ought to be at least 1% of the iPS cells people produce should be SSEA4 negative. So just as an example of a marker which should not necessarily, most of the time it'll work, but there should be times when it won't. Well, I think it depends then, well, from my point of view, it depends what you're going to do, because for different people have different points of view, as I was trying to say. If you're interested in making making dopaminergic neurons to put into a patient, you probably don't worry too much whether they'll make germ cells. On the other hand, if you're really interested in understanding early development, then you may want to know that the cell actually correlates to what the cells in the early embryo will do. So it's difficult to say generically what it should be, but I think generally over the years, the sort of bottom line is a pluripotent stem cell can make derivatives of at least all three germ layers. But it doesn't tell us which cells they'll make. That's been the traditional assay.
The functional test should be a differentiation assay, basically.
Yeah.
Okay.
So does that mean that we feel we're ready to move away from teratoma-forming assays as the paradigm and to start to accept in vitro testing as being sufficient?
Please, yes.
Well,
Please, yes.
Lady in the
All of these assays are inadequate because, the cells pass the tests, and then in the specific cell differentiations that they're being used for, they do not perform equally. We, for instance, and many of the people tell similar stories of using sets of hPSC lines or particular retinal differentiations, and they don't behave even though they will pass those processing tests. And so what we're left with is we're picking lines on purpose, which must be fundamentally different. And this is not just
so
But
I think
the other thing you have to recognize in looking at that, though, is that some of that is cell culture system dependent. So a cell line that may not necessarily differentiate to a particular lineage may differentiate to that lineage if you change the protocol or the culture system. So you're right, you can't necessarily always tell, but it's dependent on more than just the cell line itself. It's dependent on how it's managed.
so. Maybe in fact here we are not discussing anymore about pluripotency, but variability between lines, which is slightly different and makes things complicated because clearly all the cells are variable, but doesn't mean that they're not pluripotent directly.
We talked earlier, the question was asked is, are there iPS cell lines that don't, or ES cell lines that are not pluripotent? I've acquired an iPS cell line that expresses all the undifferentiated cell markers but will not make a teratoma. And so that line actually is one that I acquired for research, but it hasn't been deposited in the stem cell bank. And those are the types of cell lines that I think we need to see deposited in the stem cell bank so they can be used potentially as controls for some of these experiments. If you know it doesn't make a teratoma, but it expresses stem markers, it would be good to be able to run it alongside.
Okay. I think also there's room, as I'm alluding to, room for new assays, whether it's chromatin markers or whether it's new kinds of in vitro assays where we're looking at self-organizing organoid systems in the future, but that's it's going to be a way away, I think.
So maybe we can, because we have a lot of points to look at, so maybe we could summarize here is that, pluripotency need to be distinguished from variability between lines, can be tested functionally using a differentiation assay, can be teratomas, but teratomas is really advantageous to look at tumorogenesis and formation of tumors. And that basically, what is the test can be extremely variable depending on the application and the type of differentiation. So that could be a first point. The second point is that comparison with in vivo and early pluripotent states, and of course with human ES cells and human induced pluripotent stem cells, a vast discussion. So can we do that first? That's probably the question. Can we really compare in vitro derived human ES cells with any in vivo data set right now?
So we compare the chromatin state. So the cells we have in vitro doesn't really even come close to what's happening in vivo. But of course, in vivo, it happens very fast. They don't, stop at a particular point. So I think scientifically, I think it's important to establish equivalency. But I think technically, we're not there yet. I mean, it depends on how we're going to refine the system and whether we use the cultured embryo versus what's really the real embryo in vivo. I mean, that's the culture condition influence the whole system enormously. But that said, there are certain points cannot be influenced by the culture media, and there are certain areas very sensitive to culture media. We have to really categorize them into two categories. And that, I don't think we have with that yet. I think the community have to come together to define. I mean, they are definable. They are not totally we can really certainly map those out.
Maybe in question is, and probably important for journals, is when you do basic science on an in vitro system like human ES cells, or of course you can't validate everything in vivo. Does it decrease the value and impact of the data you generate?
No, not necessarily, because I guess if you come from a practical, pragmatic viewpoint, you can say these cells, even if they're not exactly similar to that, that environment in which the epiblast is developing, and they may not be equivalent. One question is, could you ever have an equivalent cell type? The second is, even if you don't have equivalents, is it still practically useful to have those cell lines? And I would argue, yes, they're incredibly useful if you're making hepatocytes, cardiac cells, neurons. I mean, those are really, it's still a tractable system, even if it's not equivalent.
As researchers will spend a lot of time trying to create the perfect cell that they can see in vivo. That's what they want to do. It's part of the research work. It's not necessarily what you need for a medicine. You need something that will deliver a function, some functionality, and will survive in the human subject. So that's a different question to whether you're trying to make a perfect hepatocyte or some other kind of cell. And hepatocytes are a particularly challenging aspect of this to deliver with an adult phenotype. But there may be uses for those hepatocytes clinically which are perfectly acceptable and effective. We don't have to be looking for a perfect cell every time.
It's an artificial construct anyway. We're dealing with it, we talk about, can you make it like the in vivo? It's already not like the in vivo. The in vivo, this state of pluripotency lasts a ridiculously short amount of time, and naturally the cell doesn't exist in that state. Now we have a cell line where we can maintain that state indefinitely, so we're already working with something that's not representative of the in vivo state. So.
Yes, so I agree to some extent that as long as the cell can do what you want it, so as long as the starting cell line can make the perfect hepatocyte or the functioning neuron that I'm trying to make in my studies, then that should be enough. The problem is when you take the step to use the cells in patients, we need to predict not just what this cell will do in the next few weeks or years, so we can take them in our animal models up to maybe a year, but they're supposed to stay in the patient in the brain for 30 years. So I guess part of me at least thinks that the more similar to a naturally occurring origin this cell have, the less likely is that it will do something at a later stage.
Yes, but it's a medicine, so the qualities you want to build into your medicine are not necessarily the qualities that you would have wanted in natural cell population, if I can call it that. I mean, in the case of neurons, for example, you're probably trying to get the neurons to integrate into the adult nervous system, something that never happens. It happens in a few situations, but by and large, it doesn't happen. So just to accentuate, this is Glyn's point and also raised here, one's got to make the distinction between a starting material, which is what we're dealing with here, and the actual cell therapeutic. So the critical quality attributes of your cell therapeutic are going to have to be defined very precisely without reference to ongoing in vivo situations. That's not the issue. The issue is, what are you asking that medicine to do? How do you define those properties, and how do you show that your cells have them in a consistent way? That's quite distinct from the characteristics you want to see in your starting material, which is what the pluripotent cell is for the most part.
It will be extremely technically challenging to get cells grown in vitro that are exactly similar to cells in vivo because of dynamic culture conditions, developmental stage, and so on. But at least we need to fundamentally understand what the cells that we have in our cell culture are and what are the mechanisms that control their pluripotency and differentiation, so that we are sure that when we differentiate them, we produce cell types that are functional for clinical application. Is it a good summary?
Just to say, remember, you might define a cell as being problematic from a pluripotent cell potential because, let's say, it makes mesoderm, but it doesn't make neuroectoderm, or not very well. That mesoderm-making cell may nonetheless be the perfect starting material for, I don't know, cardiac muscle or something.
Yeah, but
right?
then I think it will be essential to understand why these cells can only do mesoderm.
Absolutely, that's the scientific question. I'm distinguishing it from the therapeutic starting material question, which is actually quite a different one.
Then it becomes a matter.
The stability of the line is very important to go from that to our production center to whatever purpose. If we don't understand the basic biology of the pluripotent state, then how are we going to transform any therapies from one lab to another, or one clinic to another? So we really do need to know what the consequences are.
Yeah.
At least the risk.
Yeah. Just one quick comment on that, Christine. Actually, yes and no. As in, if that cell line is going to be used, and it's going to be used for that one particular differentiation, then you should have already set up a protocol which would allow you to do that. So the same protocol done wherever should give you the same cell. But just to add to this slightly in terms of experience, is Chef One, which I used, as you know, Peter, and Zoe's here. We used Chef One because it gave a lot of RPE. We did not use Chef 6 because it doesn't give a lot of RPE. And the reason for that is because Chef 1 goes down to a more neural lineage than Chef 6 does. So I don't want necessarily a completely pluripotent cell line. I want a cell line to give me the therapeutic product that I want. And actually a question which I've come back to you, Peter, a few times, which is this whole idea about teratoma, carcinoma teratoma. What is a way of understanding whether those cells are safe is what in your therapeutic product, if it was there, is going to be the most dangerous. And actually, I think a terocarcinoma is probably the easiest to get rid of clinically, isn't it? I think.
The only thing I would say you have to be very careful is that one focuses, people have focused a lot on teratomas, teratocarcinomas as the thing that you don't want. And they're clearly going to happen from undifferentiated cells that are contaminating. The concern is whether any genetic changes in them which might promote that may somewhere along the line actually have an effect on the differentiated cell, which we don't know, but it's something we have to consider, because the differentiated cell, if it's turned into a malignant cell by some genetic change, is a different kettle of fish altogether.
I think your point on the RPE is basically the third point, can we derive universal protocol of differentiation? By universal protocol of differentiation, that means protocol that will work with any human pluripotent stem cells with the same efficacy. So can we develop one day a protocol that allows to generate pure population of TH neuron, let's say, from any cell line that is available there, or shall we just admit that ultimately we'll have to select our lines based on their capacity of differentiation on those specific protocol and go from there?
You have to accept the reality that not all cell lines have the same potential. In my mind, there's just no question. We look at the cells that are used within across different indications that are coming out of the bank, and some just simply make different cell types better than the others, even if they're cultured in the same culture system and using the same differentiation protocol.
So going back to the differentiations, maybe what we should be doing, and potentially as part of some of the registries, is opening up a best practice file where people can lodge their methodologies with the references that support that, and people can have a repository to go to find who's doing what.
I have a comment to these different lines, because the more we understand about regulating pluripotency and making the lines, the better and more consistent the lines get. So early on in our project, we tested the available GMP lines at the time. There was quite a bit of variation in these lines. Then 10 years later, our protocols are better and more defined. We understand how we pattern the cells, and that combined with the field of making the pluripotent stem cells that better understand how to regulate pluripotency, the different stages. So then when we came with our more standardized protocol testing the new GMP lines, there's very little difference in how they respond to the patterning cues. So I think we tested 5, 6 of Frederick's lines. They all responded the same. We tested the new UK lines. We tested maybe 10 lines, and I think there was one that didn't perform. So I think that to standardize based on lines that was used in the past is probably not. I think if we waited out another 5, 10 years, it's going to be taken care of anyways, because the lines will be better, the differentiations will be more precise, and the variation will decrease. But I think that the largest variation comes in how you derive the line. So now when you don't use feeders, you don't use undefined components, there's a lot less things. So if you look at the older ESL lines, probably if you were to do all these standardized tests that you discussed on those, your variation will be quite high. If you do it on the lines that's been generated in the past 2 years, it's not going to vary nearly as much. So there might be very few things related to genetic composition that are line specific, but I think that they will be more and more similar and respond if you get the cells into if you have a naive state or a prime state. We understand more about the state of the cells, and I think that this variation is greatly reduced already, and it's just getting better.
Recognize also, though, that we're not necessarily only talking about a line-to-line variation, because there are subclones within lines. So from the same donor, just different clones that show vastly different expression profiles. So if Sushan Zhang did a look at the Jamie's first IPS lines, the IMR90s, clone 1, 2, 3, and 4, have vastly different expression profiles for OCT4. And so even within a single donor, subclones of the same line may have significant variation as well. So, but I agree that it's certainly getting better as systems improve, but there's still variation.
Yeah, I think that is actually an important point, because of course as we get better at deriving these lines and maintaining these lines, we will get less of a variability and less of a drift towards aberrant cells and so on. But I'm a little bit surprised. We all agree that the functional test is probably the most sensitive at the moment to assess stem cell quality, but in clinical settings, I think if there's a heterogeneity within the cells, then it's those cells that fail to do a certain cell fate that might cause the trouble. So if we do, say, a teratoma and we see all 3 germ layers, that's not to say that every cell was able to give rise to every germ layer. But in clinical trials, that could then be a problem. So we all agreed immediately that functional test is the best way to go. But eventually, we should be able to bring this in alignment with molecular tests, right? Because the cells are different from each other because of their derivation history, which is gene expression epigenetics, or because of their hardcore genetics. They're, you know, different people, and so shouldn't there be a more effort, you know, towards these, you know, genome-based assays, because they are simply more sensitive on the long run, possibly.
So
detect, for example, p53 mutations within the population.
Comment on that, which is the obvious one which occurred just recently was the p53 mutation that came out of the Harvard work, and also, sorry, and the work in Cambridge. And actually, you know, clinically, there was a real mass panic in terms of, look, these are GMP grade lines and they have a p53 mutation. And actually, one of those with a certain concern is H9. And H9 is in patients. But P53 is in patients. There are patients walking around with a P53 mutation who don't get cancer. So, you know, this whole idea that genetics is going to give you the all-encompassing, you know, idea of safety, I just think is wrong. We don't know an awful lot about genetics, not least the actual interaction of the genes. What's going to... And P53 isn't a cancer gene. It promotes cancer.
So I think the sense of the question were more normal genetic of the cells influencing capacity of differentiation, and can we predict from genetic variant by clear capacity of differentiation? I mean, the safety issue is I agree that we don't know what is the impact of genetic mutation and genetic changes on capacity of differentiation and safety, and that's a very big question. But so Daniel, maybe you want to comment on the genetics to close this one?
Just one of the things we were interested in scientifically, could we find evidence for either specific loci, common variants that subtly altered how lines behaved in culture, or perhaps somatic variants? I think that, and we collected a lot of lines and we looked as hard as we could, and we didn't find anything that was reproducible or believable. I think a lot of things come into play in there. Culture conditions varied a lot. It was hard to control. The assays were, it's just hard to get these assays to scale to hundreds of lines. So I think there were technical challenges, and common genetic variants have small effects, and that means we have a space where we know roughly what's required for organismal traits like height and so on. We know what's required to find genetic effects on gene expression, and those things in between, which are neither low-level molecular traits nor organismal traits, we just don't know. So it may be that hPSC was an order of magnitude too small to detect those things.
I think some people in the audience are...
But I think it's a really important summary point, is that we don't know what any of this information means at the moment. And certainly within a clinical context, we have no idea what this is going to mean. So the only way we can attack this and the only way we can look forward is by collecting that data at the outset so that we can later correlate it to, for example, clinical effect, differentiation capacity, tumor formation. So I think the take-home message is we need to start collecting those data and keeping them in a format that's usable and to a standard that's going to hold up into the future. But for now, we probably don't need to be using it, but we certainly need to be stockpiling it.
So I think we all agree that finding universal protocol of differentiation that will work with any lines will be extremely challenging. No, that may improve over time with improvement of derivation and quality of the cell line, but that the moment the current stage is still very, very challenging to do that. Instead, I think what we discuss is clearly that this variability is very complex. The origin is probably genetic, but mixed with epigenetic, and clearly we're not entirely sure what is the proportion of each aspect. But it will be good to collect information to make sure that that the knowledge accumulated on the capacity of differentiation of lines that are currently used is broadly available, and that may be through banking system. And the question around standard line. I would like to see 5 super lines that have been characterized by a broad number of labs that we know are super stable and super useful. And I don't know how we can organize that as a field, but even for I think for journal and so on, maybe I have these criteria lines could be useful at some stage. The last one is, does epigenetic memory play a role in quality or level of pluripotency? All topics which I thought was solved. No, I'm joking. No, right, so anybody have any comments on that? I mean, we did some studies on that, too, actually with Daniel in the past, and we see a bit of epigenetic memory, but it's not like...
In the study we did with you, I mean, it was well designed for the question. We got multiple lines from multiple tissues from multiple people. We didn't see a whole, I mean, I think it's how you define it, right? What we saw was not much variation could be explained by tissue of origin relative to those other things, particularly genetic background. That doesn't mean to say there is no such thing as epigenetic memory. It just means the other things explain more variability. It could be there's one locus that matters and that affects your different, but you know, our study wasn't designed to get at that. But it was certainly not, you know, more important than just regular genetic background variability or other kind of, you know, gender, things like that. But that may be because we've underestimated the importance of genetic background rather than overestimated the importance of epigenetic memory. I think it's on a relative scale rather than one thing is, you know, definitely more important than the other.
So there's a group at the Gladstone that's spent a fortune on single-cell sequencing of neural cells and different iPS lines. With many different genetic backgrounds, ethnic origins, and the biggest variable was actually the user. So there was no significant variation between all of that. The user, even within one lab, using the same protocol was the biggest variable, which is a sobering thought, really.
So if we're never going to standardize, or if we try and standardize but individual users will still do something different in the nature of innovation, which is what we all do, how do we capture that data, and what of that data needs to go with a cell line so that you can understand what it is and what it does, which I think brings us to the banking initiatives. And the top question there is there already an excellent model? Well, I think we've heard of models today that are excellent.
Maybe I can just comment on the model we have developed, which has been developed over the last 10 years in close collaboration with GLIN and the International Stem Cell Banking Initiative and the Stem Cell Forum. And that's, I think, a pretty good model. It's modular, so we have models, data models for ethics, for donor information, for cultivation and reprogramming, for genetic characterization, so genotyping, for the characterization of the cells. Is it a pluripotent cell? What is a marker expression? Which cell types can be derived or have been derived from this cell line? And we have also a module for genome editing. And here's, for example, the question which we haven't solved yet: should these gene-edited lines be tested again for pluripotency? So these models are there, and there are other models, overarching models for clinical application, for application and drug testing, or for just research application for disease modeling. So these models are there. And what I see when I look at the data models from banks, that elements of these data points we have are there, but not in this comprehensive way. So I think it would be a very nice, very useful effort to harmonize these data models and apply at least a minimum standard to banks. That also enables, what you brought up, would make it much easier to fill the registry with data, because the data are harmonized. And I just wanted to raise one more point which came up in the previous discussion. This is feedback from researchers about the quality of lines. And when I hear that Chef1 and Chef6 differ in their potency to derive certain cell types, that information would be very nice to have in our global registry, so everybody knows that, or protocols. So protocols to differentiate which work and which don't work for a specific line. So in conclusion, there is a model. It needs to be it needs more harmonization. The field is developing as well, and we need to agree on the standards which need to be considered as at least a minimum or a mandatory information we need. For example, you brought up the TAR 61 thing. Do we actually need marker expression if we have a pluripotency test? Is it a requirement at all?
So if you want to have your embryonic stem cells to be used in the United States and in projects that are financed by NIH, so they should be on NIH registry. However, if by definition of NIH, embryonic stem cells are derived from blastocysts, so no single cell derived embryonic stem cells are on registry. So even embryonic stem cell clinical trial that is quite successful in macrodegeneration is not, that the cell line cannot be registered. So it's not by definition, it's not embryonic stem cell line. So what's the point for me it's more important to get NIH registry than, because it has benefits, if I'm deriving embryonic stem cells, than to get in some other registry just for sake of be registered, because of the time involved.
But I think there's also a question now about ES versus IPS as well, and whereas with ES there were always greater requirements to register because they were linked to funding and to licensing, it's not the case with IPS, and the quality controls that go along with that.
Well, regarding the NIH lines, they are all registered also in the global pluripotent stem cell registry. So the point is to have an overview of the lines which exist. Of course, there are gaps. But if you want to search for a line which does certain things and has certain information attached to it, then you don't want to go to NIH registry, to YCell, to CDI, and to other databases. The better way would be to go to one and search all of them at once.
I think and Andreas has done some of this work before, you can link databases. There's no reason why you shouldn't coordinate databases. And that has happened in the past. And I also remember there have been a lot of databases which haven't stood the test of time. And I think HPSreg is one of the longest running now, consistently. And it's growing. So it's been quite a big success for the European Commission, and given them a governance mechanism as well.
Yeah, just to follow up on that, of course you don't need to have one central register for everything. You can link these, but for linking you need at least a common identifier. So, and this is actually the key which we provide. So the common nomenclature and identifier.
Okay, so I think we have unfortunately run out of time. So we have another session to get through before lunch. So just to summarize there, I think what we're starting to say is that we already have good registries, that we still need to consolidate registries, and maybe something like the model of the bone marrow registries that you showed, which are now global and linked, and they can be called across different registries. Maybe that's a paradigm we could start to look at and to adopt, but that we already have a good basic set there. We need to define what the minimum criteria will be that has to be accessioned. Some of that is already defined by the EU, for example. And then what additional data we would want, and whether we're now starting to think about methodologies and propensities and capacities also being added to that. Is that fair?
The background of this correctly, but at the moment in those registry, you don't have to explain how it differentiates towards whatever lineages at all. No? So I think that sounds quite something that could be easy to implement in the places where you are registering the cells. So.
To get to your point, you're not required to enter that information to get a cell line name through the registry. But in order to have the cell line validated and receive a certificate that would prove that the cell line was ethically derived and actually a pluripotent stem cell for EU funding, EU EC funding, you are required to enter that information. That's correct, yes?
Yes.
Okay. Right.
Thank you very much.
Thank you.